In this video, I'm going to apply the method of minimum potential energy to the simplest problem I can think of. A single spring attached to a wall at one point and free to move at another point, I'm calling node 1. The spring has a stiffness of K. And of course, I'm going to apply a force at node 1, and node 1 is going to be displaced by some amount, U1. As I mentioned in the last video, the first step in applying the method of minimum potential energy is to find a formula or a function of the total potential energy stored in the system as a function of the displacements. And in this problem, I only have one displacement, U1. So what I'm looking for is the function of the total potential energy stored in the system as a function of my single displacement, U1. Now, we will learn that there are two components to the potential energy stored in the system. There's the internal strain energy, and there's the potential energy due to external forces. And these are summed together. So the total strain, internal strain energy in the system as a function of my displacements. Again, I only have one displacement. And I'll explain later why there's a minus sign. But I will subtract off essentially the lost potential energy due to external forces being used to create this internal strain energy, also as a function of my internal displacements. All right? So now that we have this form, let's look at each one of these components separately. Let's first look at the internal strain energy stored in the system. What is that? Well, in this case, I have a single node that moves from this location to this location due to the fact that it's being acted on by a force. Well, that means that work has been done on it, because as you recall, work is force times distance. What is the force and the distance this is moved? Well, you might be tempted to say that, well, this force is P and this distance is U1, but that might not be totally correct, because as this force is applied, it only required a certain amount of force to move node 1 from here to here. That wasn't a force P. If I'm from here to here also wasn't some force P. The force required to move this point any distance actually increases because of Hooke's law with the amount that this spring has already moved. In fact, you can say the way the force moved with respect to distance is in fact based on if this is my amount of displacement and this is my force, we expect that the amount of force required to move some distance would be this line with a slope given by K. That's Hooke's law. Now, if I want to know the amount of work that was required to move a node from one point to another point, that would be the area under this curve. We notice it's force and distance. Displacement is distance. Force times distance equals work. The amount of differential work, dW, is given by the area underneath this curve, or in this case, a straight line. So what we say, of course, is that the total work done to move the spring to the point U1 with its, at which point the force has the value of P, is equal to the total work is the integral from 0 to U1 of K U du, or the area underneath this whole triangle. All right? Well, if I evaluate that integral, or if I just look at the geometry of the problem, I can see that this work is equal to 1/2 K U1 squared. And that work was done on the system. That work is now stored in the potential energy of the system as the internal strain energy. So I will say that my internal strain energy in this system is 1/2 K U1 squared. Now let's look at the potential energy of external forces. In order for my system to store this potential energy, I need to have this force P acting on it so that this point stays at this location. So that means that that force is being used to create this strain energy. It can't do any work itself because it can't move anything. We have reached steady state. Normally, this force could be used to move a point some distance. It could have moved it to this point from its original position to its original position plus U1. It can't do that. It's essentially work or energy that is lost and needs to be subtracted off from the system. So simply the external energy, the potential energy from the external forces is just the amount of work that could be done by moving this point, this distance, by this force. So the external energy, which I'm subtracting off, is simply P times U1. All right? And now I have my function of total potential energy as a function of U1. Now, my goal is to find the U1 which causes the minimum amount of potential energy. That's step 2 of using the principle of minimum potential energy method. How do I find the U1 that minimizes this function? Well, we've learned how to do that in a previous class called Calc 1. In Calculus 1, in our first semester of calculus, we learned that if you want to minimize a function with respect to some variable, you take the derivative of that function with respect to that 0 and set that function, that derivative, to 0. That is, what I want to do is I want to find the change in potential energy, total potential energy in the system with respect to my displacement, and I want to set that to 0. So let me go ahead and do that now. I'm going to find that change in potential energy with respect to U1 is equal to, this will be K U1, this will simply be minus P, and then I want to set my result equal to 0. Now I have an algebraic equation which I can solve for U1, and I will find that U1 equals P over K. So now I have the displacement of node 1 as a function of simply the applied force, which would be given in the problem, and the stiffness of the spring, which would be given in the problem. So I found my displacement of node 1. That's what I was looking for. And you might not be terribly excited by finding this out, because this is exactly what we would have found out for the displacement had we just applied Hooke's law to this problem. In the next video, I will apply the method of minimum potential energy to a slightly more complex problem, and I hope you will start to see the value of the principle of minimum potential energy method.